Hello everybody. The next series of presentations will be all about deflection of beams. Now we have seen the whole concept of beam. The whole concept of beam was like this, that if there was a beam like this, and if it was some sort of a simply supported, let's say, beam, and if it was loaded by some kind of transverse loads, right, then the beam essentially develops certain internal stresses at every cross section, right? And those internal stresses are essentially the bending moment and the shear stresses. And the beam, due to this loads, deforms, right? And this deformation is like this, right? Now, we know what is pure bending. In pure bending, we have seen that essentially the bending moment remains constant at every cross section. That is, essentially, the bending moment remains constant at every cross section, or the shear force is zero. Now, if we have analyzed the whole concept of beam taking this pure bending, right, taking this assumption. Now, we have seen that if pure bending at all happens, then M by I is equal to nothing but E by R. And if I bring E to this side, essentially I have this relation wherein M by EI is equal to 1 by R. And this R is nothing but the radius of this I should say, if it bends in the form of a circular arc, R represents the radius of this circular arc, right? So R is basically, if this is one circular arc, R is this. Now, in case of non-uniform bending, essentially what happens is that this bending moment M is not constant throughout the cross section. So essentially R also varies, right? So what we do is that to analyze non-uniform bending, let us assume that this deflected portion of this curve will not be in the form of a circular arc, right? So essentially, because this R will be different, because M is different at every cross section, and at every cross section, if M is different, R must be different. So in case of non-uniform bending, we cannot assume some kind of a circular arc. Now let us assume that we have, suppose this is my x-axis, let's say, and this is, suppose, my y-axis. Now I have a beam aligned to the x-axis, and let us suppose that it is subjected to some sort of a non-uniform bending, and essentially the elastic curve is, suppose, like this, right? So essentially what happens is that if we take 2 points, let us say if this is A and this is, suppose, B, and the distance between this point is nothing but is equal to ds, right? If we take these 2 points and essentially if we draw tangent to this curve at A and tangent to this curve at B, essentially it meets, suppose, at point O, and this angle is, suppose, d theta. Now we know that that thing, that is M by EI, is equal to, we know, is equal to 1 by R. Now as A and B are 2 points whose distance is not that great, that is only ds, or an infinitesimally small distance, therefore we can assume that the moment or the bending moment is not changing that much in this length. So essentially we can use this equation right now. Now we know that R essentially is, suppose, this, right, and R d theta is nothing but is equal to ds. So we can replace 1 by R in the form of d theta ds. Now in case of this, right, this is essentially a deflected portion in an elastic sort of a curve. That is, this deflected curve will be some kind of elastic curve, that is, the material of the beam will be still elastic, right? So essentially that does mean that there will not be that much deflection. So essentially, let's say that if there is at all not that much deflection, we can assume that ds is approximately equal to dx. So we can write ds in terms of d theta dx. Now what is this theta? Theta represents the ratio of the change of this deflection with respect to the length of the beam, right? If y is the deflection and x represents the length of the beam, then theta, that is dy dx, gives me the slope of this deflected curve. So essentially what I can write is, I can write this in the form of d2y dx2, right? So what I have is m by ei is essentially y double dash, and this is a differential equation that we have for this elastic deflected curve. Now two assumptions that I made an assumption, or we made an assumption in the theory of bending, that essentially this relation, that is m by ei is equal to 1 by r, holds true if the beam is elastic. So I have derived this relation from this. So essentially this deflected curve will have this relation when the beam is within the elastic range, that is the material is within the elastic range. So this relationship holds true if the material is within the elastic range. Now we see that what will be the sign? If there is some sort of a sagging moment, as we can see here, which is concave upwards, if there is some sort of a sagging moment like this, then essentially this m will be positive, right? But theta, or I should say this d theta dx, which is basically nothing but d2y dx2, d theta will be an algebraically decreasing function with x. That is, we will have consistently lower values of theta as we progress. So essentially d theta by dx will be algebraically decreasing, and hence d2y dx2 will therefore be negative in case of a sagging moment. But in case of hogging moment, things are different, because m is negative in case of hogging moment, whereas y dash dash, in case of hogging moment, it will be some kind of a thing like this. So essentially, as we can see it clearly, that theta will be an algebraically increasing function of x here. And if it at all is an algebraically increasing function of x, so d2y dx2 will be essentially obviously be positive. So this will be again then positive. So what we have basically is that if m is positive, this will be negative. If this is negative, this will be positive. So we can generalize it, and we can write this in the form of m by ei minus y double dash, right? And m, if it's positive, sagging, we take it positive. If it's negative, we take it negative. So this is my general equation, and this thing is the sign convention. The next thing that I'm going to look at is try to find out the deflection and slope, and try to see this with the help of an example, right? Let us assume that we have a beam like this, right? A simply supported beam like this, wherein one end is placed on a roller and the other is placed on some kind of a hinge support. It's pretty clear that this will be some kind of a statically determinate structure, as there are three equations of equilibrium and two unknowns here, one unknown here, so there will be three unknowns. So we can solve this and we can get the reactions out. And as all the forces are acting along the y-axis, if this at all is the y-axis and this is x-axis, therefore we can say that this reaction, this is symmetrical obviously, the total load being WL, we can divide it into two parts, and the two reactions will be essentially WL by 2 and WL by 2, right?